In this video, we are going to do an example of the analysis of a simple circuit containing resistors in series and parallel. So the circuit that we are going to be analyzing is this circuit shown at the very top here, which contains 6 resistors, and those resistors have a resistance of 5 ohms each, and it contains a battery which has a voltage of 20 volts. So the first thing that I do when I look at a circuit like this is I find these diagonal wires to be somewhat confusing. So I redraw the circuit with only vertical and horizontal wires. You don't have to do this, but I find it helpful for myself. So I've labeled each of the resistors 1, 2, 3, 4, 5, 6. They all have the same resistance of 5 ohms, but just so we can match them picture to picture. So at the bottom of the screen here, I have drawn the exact same circuit, just with only lines parallel. Because this is a diagram, the direction that the lines go in terms of whether they're diagonal or horizontal doesn't really matter. It's just the relative series parallel nature of the lines that matters. So we start out at the battery, and then we move to the right and up, right? And we get a resistor where all of the current that flows through the battery must go through this resistor, right? So this resistor here is in series with the battery. That is this resistor 1 here, which I've highlighted as red. It's in series with the battery in both pictures. Okay. Then we get to a junction C. At junction C, the current can go one of 2 ways. First, it can pass through only the second resistor and then go back to the battery. So I need a path that goes from C through only the second resistor and then back to the battery. And that's what I've drawn with this one horizontal line here for resistor 2. So notice that if you kind of cover up the left-hand side of my top circuit here, so you cover up all of the left-hand side of the top circuit, it is the same. It is a circuit where you go through one resistor, then you go through the second resistor. So you go through resistor 1, you go through resistor 2, and then you end up back at the battery, right? And then if you ignore the top part of my lower circuit, it looks the same, right? You just have 2 resistors which are in series with the battery. So that looks good. Okay, if we go the other way, then we see that all of the current that goes the other way goes through R3. So my third resistor, everything that doesn't go through R2 must go through R3. Right? And then my point here, I'll make it black. My point here is point B on the upper drawing, which I can highlight here. So then I get to a junction where either all of my current can go through R4, like this, or it can go around through R5 and R6, like this. So I get an option to either go through R4, which is my yellow path, or it can go through R5 and R6, which is my red path. And then both of these are connected back to point A. Right? All things here connect back to point A, just like they do on the upper circuit diagram. So I find the lower one easier to work with. The upper one is exactly the same. That's your call. Okay. So our goal now is going to be to find the equivalent resistance of all of the resistors together. That is, we would like to be able to draw a circuit which is a battery with just one resistor, which has the equivalent resistance of 1, 2, 3, 4, 5, and 6 all together. Because once we've done this, we can find the current through the battery. And once we know the current through the battery, we can start building our circuit back up to find the current and voltage across each of the resistors in the circuit. So that's our end goal. And to do that, what we need to do is we need to look at our initial picture here, and we need to see if we can find any resistors which are uniquely in series or uniquely in parallel with one another. So, for example, 1 and 3, you could think, oh, those might be in series with one another because things go through 1 and then goes through 3. But our criteria is that if you are in series, all current that flows through one of the resistors must flow through both. So all current that flows through one of the resistors must flow through both if the resistors are in series. And we can see that that is not the case for 1 and 3. All of the current that flows through 1 does not flow through 3 because some of the current gets redirected into resistor 2. So 1 and 3, for example, are not in series. They're also not in parallel. So our requirement for parallel is that the two resistors have the same voltage. And I say 2, but it could be any number of resistors. It could be 2 resistors, it could be 5 resistors, however many. So our two options are that they are in series if all of the current that flows through one flows through the other, and it must be true for both. So all of the current that flows through 1 does not flow through 3. Even though all of the current that flows through 3 has already traveled through 1, they have to both be equal. They have to have exactly the same current in both resistors. All right? And in parallel, they have to share the same voltage. Now, the only things in this circuit right now that are uniquely in series or parallel with each other are resistors 5 and 6 here. Those resistors are in series because any current that flows through 5 must also flow through 6. So we can write R5, 6 using our series addition formula is just R5 plus R6. And since they both have a resistance of 5 ohms, this is just 10 ohms. So now what we can do is that we can redraw our circuit where we replace 5 and 6 with 5, 6. So now what I've done is I have redrawn our circuit, but I have replaced the two separate resistors, 5 and 6, with one resistor with their equivalent resistance of 10 ohms. So now we can repeat this process by looking for any two other resistors which are uniquely in series or parallel. And what we find is that these two resistors here, R4 and R5, 6, look like they are in parallel with one another. One easy way to tell if resistors are in parallel is if you can connect the two sides of them via a conductor. So the right side of these two resistors, I can connect via a conductor without going through any other resistor by my red shaded region. Likewise, the left side of these two resistors, I can connect via a conductor by the blue shaded region. So the left sides of the resistors are connected and must be at the same voltage. The right sides of the resistors are connected by a conductor and must be at the same voltage. Now, the left and right voltages are not the same as each other, but the right side of R56 is at the same voltage as the right side of R4, and the left side of R56 is at the same voltage as the left side of R4. And that is our definition of parallel, right? They have the same voltage drop across them. The voltage difference between the two sides of both of the resistors is the same. So we can find R456, the combination of these three, by using our resistors in parallel equation, where the resistors add as 1 over their resistances. So 1 over R456 equals 1 over 10 ohms plus 1 over 5 ohms is going to be 1 over 10 ohms plus 2 over 10 ohms is going to be 3 over 10 ohms. So R456 is going to be 10 over 3 ohms, which is 3.33 ohms. Notice that this value is lower than any of the resistors of the individual resistors in parallel, right? So 3.33 is lower than 5 ohms and it's lower than 10 ohms. You will always find a value for the resistance that is lower than any of the resistors that are in your parallel circuit. Okay, so now what we're going to do is we are going to replace R456 with, or R56 and R4 with R456, an equivalent resistance there, and we're going to redraw our circuit. Now we can write our circuit with R456 inserted in place of the individual resistors 4, 5, and 6. And we're just going to repeat our process again, where we look for any resistors which are uniquely in series or parallel with one another. And here we can see that these two resistors are in series because any current that goes through R3 must also go through 4, 5, 6. So we can find R3, 4, 5, 6 by simply stating that is R3 plus R4, 5, 6. Since R4, 5, 6 is 3.33 and R3 is 5 ohms, we get 8.33 ohms for the equivalent resistance of R3, 4, 5, 6. And now we can again redraw our circuit with 3, 4, 5, 6 replaced for those two resistors. Now we have our circuit with our 3, 4, 5, 6 in place of all of the combination of 3, 4, 5, and 6. And we can see that that is now in parallel with R2. And so we can find the resistance of R2, 3, 4, 5, 6. And we use our inverse relation here. So we can say that that is 1 over R2 plus 1 over R2, 3, 4, 5, 6, 1 over 5 ohms plus 1 over 8.33 ohms. And I don't have a quick way of doing this one in my head, so I'm going to have to actually use a calculator to do it. So these two added together equals 0.32. And the units of that is inverse ohms because ohms is in the denominator. So I put a little -1 on the ohms there to indicate that it's in the denominator. R 2, 3, 4, 5, 6 then equals 1 over 0.32 because I need to get it into the, or I need to get R 1, 2, 3, 4, 5, or 2, 3, 4, 5, 6 into the numerator, and that equals 3.12 ohms. And so now we can finally write our circuit in terms of just R1 and R2, 3, 4, 5, 6. And now we can combine the final two resistors, which are in series with one another. So our total resistance, equivalent resistance of all of our resistors together is just going to be R1 plus R2, 3, 4, 5, 6, which is going to be 5 ohms plus 3.12 ohms, should be plus, which is going to be 8.12 ohms. And we can draw this circuit as simply one resistor with a resistance of equivalent to all of the resistors together of 8.12 ohms. Now, we know the voltage of our battery is 20 volts. So from there, we can find the current through our total resistance resistor, right? So I, 1, 2, 3, 4, 5, 6, is going to be the voltage divided by the resistance of my resistor, which is going to be 20 volts divided by 8.12 ohms, which is equal to 2.46 amps. And now what we can do is we know the current through our resistor. We also know that this is equal to the current through the battery, because all of the current that flows through the resistor must also flow through the battery, since they are clearly in series. Now what we're going to do is we're going to step back a level until we have, one by one, until we have reached our initial circuit and we have the current and voltage for each element in our initial circuit. So there is nothing more to learn from our most basic circuit at the bottom here, but we can step back up to our circuit at the top where we have kind of taken R1 out. So now we have written out our circuit that is split into R1 and R2, 3, 4, 5, 6. And we know the resistances of each of the resistors, and we also know the current through each of the resistors. The current through both of these resistors must be the same as the current through the battery, since both of these resistors are in series with the battery. So we know their current, and from there we can find the voltage of each. So we find that the voltage of the 2, 3, 4, 5, 6 combined is 7.67 volts, and the voltage of the R1 is 12.3 volts. We can also do our double check to see that when we add up our total voltage drop across both resistors, it adds up to 20 volts. Now you'll notice that this actually adds up to 19.97 volts. And the reason that we didn't exactly match 20 volts is because we've been doing some rounding. So our numbers here, these are not exact numbers. And so every time we make some kind of a round here by writing down a decimal answer, it changes our resistances and currents by a little bit, and that kind of adds up to a bit of error here. This is not a huge problem for us. If we really kept track of every single digit, or we left everything as just ratios, we would get exactly 20 volts here. The problem is that life gets pretty messy, actually, if you don't write down these as digits, such that you can keep track of them individually as a number. This is one of the areas where keeping everything as a variable actually isn't terribly helpful, just because the expressions get so unwieldy. Anyway, this works out to be 20 volts for our total voltage drop across both resistors. And now we can step back one further and we can break our 2, 3, 4, 5, 6 into its sub-resistors. So now we have stepped back one more level of complexity here, and we've separated R2 and R3, 4, 5, 6 into two separate resistors, which are in parallel with one another. Because they are in parallel with one another, we know that they share a voltage. Resistors in parallel have the same voltage across them. Because we know the resistance across the combined resistor, we know the voltage across each of the separate resistors here in parallel. So from this, we can actually find the current through each of our resistors. Using just Ohm's law, I2 equals V2 over R2, and I345 equals V345 over R3456. Sorry, 3456 for each of those. Finding our currents. And we know as well that because we have some current I1 coming in and then splitting into two other currents, that the sum of those two currents must equal the current coming in. So when we add these two together, we get 2.45 amps. Now, if you remember from our previously, we found that the current I1 was 2.46 amps. This is again just a rounding error based on us not keeping every single digit of all of our calculations. And we're not really going to worry about it. This is satisfying our Kirchhoff's law number 2, and we are ready to move on to the next step of complexity in our circuit by breaking up our 3, 4, 5, 6. Now we have stepped back one more layer of complexity, and what we're going to look at is separating R3 from R4, 5, 6. We know the resistance of each of these resistors individually. We also know that because they are in series, they share the same current. So the current that we found in the last part for 3, 4, 5, 6 must be the same current that is in I3 and in I4, 5, 6. That is 0.92 amps. We can then find the voltage in each of these resistors independently using Ohm's law. And finally, we can check that the voltage of the two add up to be what we expect. That is, the voltage for our 3, 4, 5, 6 should be equal to the sum of the voltage for our V3 plus V4, 5, 6, which is what we find, right? So the 7.67 number came from our last circuit where we found the voltage across those resistors together. Now we're ready to break up our 4, 5, 6 and try to get closer to our final circuit. And now we are almost done. We have moved back one more set in complexity and separated our 4 from our 5, 6. So we're here. And we've written down R4 and R5, 6. We know that these two are in parallel, so they must share the same voltage. So the voltage that we found in our last circuit, 4, 5, 6, must be equal to the voltage of each of these resistors individually. And then from there, we can find the current through each of them using Ohm's law. And finally, we check that the voltage or the current passing through these two resistors is equal to the current passing through R3, which we know to be 0.92 amps from our previous work. And when we add up our currents, we in fact find the correct current that we found previously. So now we only have one more step, which is to separate R5 and R6, and then we will know the current and voltage through every single resistor in this circuit. And finally, we have arrived at our original circuit with every single resistor explicitly written out. And the only things that we have not fully solved yet are R5 and R6. We know that they are in series, so they must share a current, and we know what that current is from our previous work. Using this shared current, we can find the voltage across each of those resistors as 1.535 volts. And we can find that the sum of these two voltages equals the voltage of v4.5, which was the combined voltage of the two. So we would expect that the sum of the voltages across each of the resistors equals the combined voltage that we found across both of the resistors, which is what we in fact find. And just as a final wrap up, I have listed all of the voltage and current numbers separately for each resistor so that you can check your work if you want to go through this problem on your own.